Okay. I believe you remember what we discussed last time, and we'll continue. So I think last time we talked about the state space, and we were talking about the operators. So we have talked about operators. Then we talked about linear operators, and then we defined adjoint of an operator. So we defined adjoint of an operator by using the definition of inner product. So suppose if you have a function phi of x, and then you have an operator a, and this a is acting on psi of x, the inner product of this will be same as the inner product of a dagger acting on phi of x. Yeah. So this is the definition. So a dagger is called adjoint of a. Okay. So now you can. We had seen last time that if you are considering vector space of functions, that is on L2 of R, that is square integrable functions on the real line, we had shown that d by dx, if you take this operator, the dagger of this one is minus d by. And I think I will repeat what I wrote. That is our second point, that is uh, physical observables. Physical observables essentially, these physical observables are properties. Physical observables are represented by Hermitian which can also be called as self-adjoint operators acting on the state space. That means we can say that if you have a situation where a dagger is same as a, then we say a is Hermitian, or it is also called self-adjoint. So physical observables are represented by Hermitian operators. Physical observables like position, momentum, angular momentum, energy. These are our physical observables. So all these physical observables, they are represented by Hermitian operator. Okay. Now, these Hermitian operators have got certain interesting properties. One of the property that we can see that the eigenvalues eigenvalues of a Hermitian operator are real. I'm not going to prove this because the proof you can find from any textbook. So let me not spend time on giving you this proof, which is rather trivial from the basic definition of the thing. Then the next result is eigenstates eigenstates of a Hermitian operator corresponding to distinct eigenvalues are orthogonal. Now, if you say that, suppose let's say you have a function f of x and then another function g of x, and if their inner product is 0, implies f of x and g of x are orthogonal. This is how the definition of orthogonality will be orthogonal. Okay, this is orthogonality definition. Second thing is that suppose if I have an operator A, and then if it is operating on some function f of x, this will become g of x. This is the most general action of an operator on this function. Okay, so this is so the A is actually a function, is a linear transformation from h to h. It will take some member of h and give different number of h. This is how the operator is understood. Now, there exists some operator. Okay, so there exists a set of functions, which I will call it as some phi n of x, and your n can go from 1, 2, etc. up to infinity. There can be a set of functions such that when A is acting on any one of these functions, let's say A on phi n of x, the function will not change, but it will simply get resized. That means it will be multiplied by some some kind of a scalar quantity A. Now, if this is the situation, then we say this phi n of x as an eigenfunction of A, and this an as eigenvalue of. So there will be certain functions like this. which are eigenfunctions of this operator with corresponding eigenvalues. Now, these theorems are telling you that if A is Hermitian, that is, if A is Hermitian, that means if A dagger is equal to A, then we have the result A is that AN, these are real, these are eigenvalues, and if AN is not same as some AM, implies phi n of x comma phi m of x are orthogonal. That's what the second theorem says. Now you can ask a question that if you have a set of orthogonal functions, let's assume that for simplicity, let us say that so this there is also another language. This AN, the set of eigenvalues, is also called spectrum of A. Spectrum of A. Okay, so these are eigenvalues. Sometimes people call eigenspectrum or simply spectrum. Spectrum of A. So let's assume that. Assume that all eigenvalues of A are distinct. All eigenvalues of A are distinct. What does that mean? That means that all the eigenstates of A are orthogonal to each other. Eigenfunctions of A are orthogonal to each other. That's what it means, right? So in that, so this also, there's another way of writing this, that spectrum of A, we say, is non-degenerate. That means there are no two eigenvalues that are same. So we say that A is having a non-degenerate spectrum. That means all eigenvalues are distinct. So this implies that all eigenfunctions of A are orthogonal. Now, suppose if each eigenfunction, we have learned how to normalize each eigenfunction. If we are also normalizing each eigenfunction, then we can say that if they are orthogonal, but they are also orthonormal. That means and normalized, and if normalized, then we say that the set phi n of x is orthonormal. Now you can, from whatever understanding that we have in vector space, if some set of functions are orthogonal, then they are linearly independent, and any set of linearly independent vectors whose number is same as the number of or the dimension of the vector space, they become a basis for the vector space. So this implies that the eigenstates of the Hermitian operator. Okay, so this is something which I will write it here. The proof we will not worry. Phi n of x is the eigenspectrum of A. It forms a complete orthonormal basis of the Hilbert space H. What does this mean? This means that and this statement, this is true with respect to every Hermitian operator. We may have some Hermitian operator for which the spectrum is not non-degenerate, but even in that case, we have to do some work, but we will be able to write down a set of eigenstates which form a complete orthonormal basis for the Hilbert space. Now, this is somewhat important to understand. This implies what does this mean? This means, suppose if psi of x is an arbitrary state in H, okay, say an arbitrary state, okay, then because this phi n of x is, I will write shorthand notation, is an orthonormal basis for H. That means this particular function can be expanded in terms of the linear combination of these basis functions. This is like a Fourier series. So if you have a periodic function here, then it can be written in terms of cos nx and sin nx. That is exactly same concept as what we do in Fourier series. So this is the basis, and any function, it is like any vector in three-dimensional space can be written as something into I plus something into j plus something into k, where I, j, k are the basis vectors. So same way, any function can be written in terms of this orthonormal. Now, the coefficients of expansion we can obtain exactly like what we used to do in Fourier series. So what you have to do is you take an inner product of this psi of x with, let us say, some phi m of x. So take phi m of x and psi of x. So that will be equal to sum over n. The Cn is some coefficient, a complex number, and the function is going to be phi m of x and its inner product with phi n of x. Now, by definition, this inner product is, since phi m's are orthogonal, this is basically sum over n, Cn into, you will have a delta mn. So that gives you simply Cn. Only when m equal to n, this summation will survive, and that value is Cn. So you can get the coefficient of expansion by simply taking, so your Cm is essentially an inner product of phi m of x and psi of x. Okay, so this is nothing very new. For example, suppose if you say that you have a vector v, which has vx times I cap plus vy times j cap plus vz times k cap. Suppose if you have a vector like this, suppose these are components, right? So these are components Vx, Vy, and Vz are components. Suppose I want Vx. How do I get Vx? I take I dot V. That will be my Vx. So same thing, I want Cm. This Cn are like components about every basis direction. So I want component Cm. So I take an inner product. Dot product is now generalized as inner product. So I take inner product with that particular unit vector. This m is like a unit vector. Dot this psi of. So it is the same concept that we know in vectors, except that so the generalization, because we have seen in the last class that this inner product is defined in this fashion. So if you want to calculate Cm, then you have to take the definition of inner product, that is phi m star of x into psi of x into dx. So you do this integral. This is what we do in Fourier series, right? So you take cos nx and multiply with the function, then you will get the coefficient of cos nx. You take sin nx and multiply with the function, you get the coefficient corresponding to sin nx. So the same concept like what we are familiar in Fourier series and also in the vectors. Okay, so this is an important thing that we have to understand, that the eigenspectrum of every Hermitian operator forms a complete orthonormal basis for the Hilbert space or the state space. Okay. So now we come back to the question. So what is the advantage of this one? Now the advantage is that so let us write this as our third point. The third point is that suppose, let's say we have a system. Okay, so let us say that we are interested in we want to measure. We want to measure a physical observable. Basically, physical observable is some property, as we said. We want to measure a physical observable. I am going to call that as A of a system. Okay, using I will call this as some meter. Okay, so some kind of an apparatus or an instrument. Okay. Now, quantum mechanics, the formulation of quantum mechanics is such that so when you try to measure this observable A, then your meter will show some reading, right? So the result of the measurement, result of the measurement actually you cannot say what is the result of the measurement. The result of the measurement it belongs to the set of eigenvalues. What is going to be the result? That is something which we cannot say, but the result is that implies the result is or what you read in the meter is one of the eigenvalues. One of the eigenvalues. Only this much we can say. We cannot say anything further or anything better than this. We can say something better than this, but about the result, we don't know the result, but we only know the set of possible results. Okay, this is like coin toss. When you toss a coin, you don't know what is going to be the outcome, but you only know that the possible outcomes are head and tail. In the same way, we only know the possible results. Possible results are eigenvalues, but we do not know what is going to be the result. This is the characteristic indeterminism that we are that many people talk about in quantum mechanics. We will not know what is going to be the result. The result cannot be predicted. Okay, the precise result is not known. Only thing is, we know that we will know the precise result only after we see the result. Okay, so uh, result cannot be predicted. Cannot be predicted. Okay. Not only that, there is also another issue. Let's say that uh, let's say that we prepare a system. Okay, so let us take some concrete example to understand this. Then I think we can generalize it. So let's say that all of you might have studied this problem of particle in a box. This is something which you would have studied, and this one has got energy E1, and then there is an energy E2 and energy E3, like this. There are infinitely many energy levels. Let's say this is 0 and this is L, and corresponding to this energy E1, you have got a psi1 of x, and let's say this is psi2 of x, and so on. These are eigenstates of energy, that means Hamiltonian eigenstates. So let us say that consider a particle in one-dimensional box, let's say 0 to L. Then this problem is something which you have done. So I'm just borrowing your knowledge. Let's say these energy levels are given by n square into E1, where E1 is given by h bar square pi square divided by twice m L square. So this is the energy of the first ground state, and then excited states are related to ground state by this fashion. And you have psi n of x, which is given by square root of 2 by L, which is the normalization constant, and sine n pi by L into x. These are energy eigenfunctions, and these are energy eigenvalues. Suppose, let us say that let the state of the particle E. Let us say that this state I am going to call it as phi of x, which is given by 1 by square root of 3 into psi 1 of x plus square root of 2 by 3 into psi 2 of x. Suppose this is a legitimate state. Okay, this is a valid state. Suppose the particle is in this state. Okay. Now what happens if you measure the energy? Okay, so now let's say you measure energy. Measure energy. Then what can you say about the result? We can say the result belongs to this set, because there are psi 1 and psi 2 in this, so it can be E1 and E2. You can say only this much. What is going to the result? We cannot say a priori, we can only say a posteriori. In the sense, only after seeing the result, we can say whether it is E1 or E2. So the knowledge that we have is only this much, that it belongs to this. Okay, so but quantum mechanics gives you a little more information. The next level of information that it tells you is that probability of E1 is equal to 1 by 3 and probability of E2 is equal to 2 by 3. That is modulus square of the coefficients. The coefficient is 1 by root 3, this is root 2 by 3. These are like square roots of probability, and probability will be mod square of that one. So suppose if you consider, let's say I have several particles. Okay, so let's say I have several particles, and each particle is made in the same state phi. So this is the state of this particle is phi, etc. They are all identically prepared. Now let's say from this source, one particle is coming. Okay, then you measure A. You measure A of this particle using some kind of a meter here. Okay, so this I will call it as some A meter, let us say. So you measure this particle, and then after doing this measurement, you forget about that system, then send another particle. So you are going on measuring this A, and what happens in this process is that in each measurement, okay, so in each measurement, so result of each measurement is either E1 or E2. Okay, so we do not know, and the result appears randomly, either E1 or E2 randomly, because we have no control on this. We have no way to predict. So E1 or E2 randomly. The only thing it confirms to is that these probabilities. That means if you are sending a large number of particles, 1/3 of them will be showing you the result E1 and 2/3 of them will be showing you the result E2. Only that is what is guaranteed, and that is what quantum mechanics tells us. So now you can ask a question. So what can we say about the property A of the system when the system is in state phi. Okay, and when you are measuring, you are getting different values. But what can we say about this property A? Now, since there is a random variation of the results, the only natural thing that one can talk about, let us say that we are sending n number of particles. So first particle has got a result as E1. Second particle from this source, I am saying. Second particle, let's say, has got E1. Third particle is E2. Fourth particle is E1. Fifth particle is E2. Like this, you have certain n number of particles, and let's say this is E1. So the result is going to be either E1 or E2. But and if you do this exercise in the limit this n is a very large number, then you can say the number of times. Okay, so the number of times E1 comes divided by n should go to 1 by 3. Number of times E2 divided by n should go to 2 by 3. This is in this limit. Okay, in this limit, this should happen. So we can define. So so the property A So what we say in this case is that we say that this property A is dispersed. We say that this property A is dispersed in the state phi of x, because we are not getting uh, one result. The result is dispersed. It can be E1, E2, etc. Now, whenever the property is dispersed in a state, which is usually the case, uh, so I would like you to think when it is not dispersed. We will come to that, but you can think in the meantime. Whenever it is dispersed in the state, the property A for state psi, state phi of x, is actually average value of all these results. Average value of all these results. Okay, it is exactly like when you are doing an experiment. Let's say you are trying to measure some quantity, you do several times and take the average of that experiment, right? So in the same way, you can talk about average value of all these results. And this average value is what you define, you call in quantum mechanics as expectation value. Expectation value. Okay, so let's say that so in general, suppose if you have got psi of x, okay, so I don't want you to get confused with this notation, because here I am now going back to this general scenario. So this particle in a box thing is done. In the general scenario, I am going to call the state to be psi of x, okay, and the basis to be phi n of x, okay. Somehow I should have used the same notation, but here I have interchanged. So please don't get confused. So now I'm going to talk about continue the discussion with the general case. Okay, so let me go back to this. So let's say I have a general situation that the psi of x is written as sum over n Cn into phi n of x. Okay. Now, result of A that belongs to the set of eigenvalues. Correct. Now, what we can say about the probability of An is actually given by modulus of Cn square. That is what we wrote here, right? 1 by 3 and 2 by 3. So in this case, if you have Cn, that is modulus of Cn square. So the expectation value is expectation value of A in state psi of x is defined as, so we denote it as A within angular bracket like this, and then that is given by the inner product of psi of x and A on psi of x. Okay, so this is not very difficult to understand. Supposing if you want to understand this, let us say that we use this notation. So 1 psi of x So let's say this can be written as, so let me call this as sum over m Cm star into, sorry, Cm into phi m of x and A operating on sum over n Cn into phi n of x. I have to use a different index for summation because there can be cross terms. So there is no star here. Okay, so now if I have to expand this, okay, remember these are eigenstates of A. So this can be written as sum over m comma n. There are two indices, and I can write down Cm star into Cn, and then an inner product of phi m of x and A acting on phi n of x. Okay. Now, what is A acting on phi n of x is the eigenvalue an into phi n of x. So that means I can now write down sum over m comma n Cm star into Cn, and this is phi m of x, and this is an into phi n of x. Okay, so that essentially means that we can pull out an as we discussed last class. It is linear in terms of this thing. So Cm star Cn into an into phi m of x comma phi n of x. Okay. Now, but what is this? This is an orthonormal basis, so that will be equal to sum over m comma n Cm star into Cn an into delta mn. So one of the summation, only when m is equal to n, it will survive. This implies I have sum over n modulus of Cn square into an. But what is this quantity? This quantity is essentially sum over n an into probability of an. So this is the definition of statistical average. So in quantum mechanics, the expectation value of any operator is postulated like this, which essentially is the average value of the possible eigenvalues that will come as result. So this is one of the postulates of quantum mechanics. It is called the expectation value postulate, and that is because you have the results of any observable are not known. They randomly, you get dispersed results. Okay, so this is one of the important aspect. Now the point is that the two things that I want you to appreciate. One is that the orthonormality, this property that we talked about, that this part, that is the eigenspectrum of every Hermitian operator forms a complete orthonormal basis for the H. This is important. Okay. Then the second thing is that the measurement results are dispersed in general, and when they are dispersed, then you have to take the average value to describe what is the value of the property for that particular state. Okay, so these two are important things. There is okay. So there are certain things here which I little bit ignored, but I will come back to that and try to understand that a little better later. But let me proceed and then talk about the fourth point. So this is also related to measurement. Okay, so this is also related to measurement. So suppose, let's say that I have a state psi of x, which is given by sum over n Cn into phi n of x. Okay, so I'm trying to say I'm going to measure A, and where this phi n of x are eigenstates of eigenfunctions of this K with eigenvalue A n phi n. Okay. Now what happens is that this suppose you measure A, so that is I have one system. So let's say I have a system like this, some kind of a particle or a vehicle. So this is coming, and then you are measure A. So this is the state of this particle is psi of x. Now you measure A, and then you get the result. As, let's say, some AL. Let's say you get the result as AL. This we can see the meter. After seeing the result, we found that it is AL. Then you can ask the question, what is the state? This is post-measurement state. Okay. Now it turns out that when you have the psi of x here, it has a linear combination of all these phi n of x. But after you get this result AL, the state, you ask this question, the answer is, the state is phi L of x. That is the eigenfunction corresponding to this eigenvalue. Okay, so this phenomena is called wave function collapse, or state reduction, or sometimes is also called a quantum jump. Okay. So wave function collapse or quantum jump, or it is called a state reduction. Now the point is very simple to understand. So you can see it in the following way. So suppose if you have, so let's say that we have a particle, okay, and then let's say the state of this particle, let's say, is phi p of x. Let's say, okay, phi p of x, and then now you measure A. You measure A. Suppose you measure A. Now what happens? The result. So the result is AP. There is no ambiguity here because result is AP with the probability one. That means there is a certainty. What is this AP? AP is the eigenvalue corresponding to this eigenfunction phi fp. So whenever the state, that is, let's say, imagine that you have a meter here, and the system that is the quantum systems that is coming to this measurement apparatus, if that is in the eigenstate of the operator that you are measuring, then the eigenvalue of that corresponding eigenstate will come as the result. There is no other result that is possible here. So in this particular situation, we say that A is sharp. A is sharp in this particular phi p, because we are getting only one result and there is no dispersion here. Okay, so one can say A is sharp. Now, what happens to the state after the measurement? State is phi p only. There is no change. It is phi p of x only. There is no change. Okay, this is one scenario when A is sharp in this state. The other scenario, so that means if the incoming state is eigenstate of A, then the result is corresponding eigenvalue. Okay. Now look at this situation. That is, you compare these two situations, this situation and this situation. Here you have an arbitrary state psi of x, and you are measuring A, and you get a result AL. You are getting one of the results, but this AL can be A1 or A2 or A3, anything, because you don't know what is going to be the result, because in this particular case, what is called A is dispersed. A is dispersed inside. A is dispersed in psi of x. So because A is dispersed in psi of x, we do not know what is going to be the result. But let's say after seeing the result, you know the result is AL. Then you ask what is the state? The state is the corresponding eigenstate. Here, if you already have the eigenstate, then the result is corresponding eigenvalue. If the result is one of the eigenvalue, then the state is corresponding eigenstate. So this is what happens in the wave function collapse. Okay, so just to give a kind of a concrete example, this is a given measurement. So let's go back to this case of particle in a box. So suppose suppose you do a measurement, and let's say that let the result be E2, then the state is psi 2. It is no longer phi of x. After this, after the measurement, the state changes. This is what is to be understood, and this change of state is so measurement alters the state of the system in irreversible manner, irreversibly. Okay, so that means some information is lost in this process. Measurement alters the state of the system irreversibly. Of course, for the last 90 years, 100 years, people are trying to understand what is the best mechanism to understand this wave function collapse. What is even though there are some interesting open questions that people are still looking at this issue. So this is one of the very profound aspect of quantum mechanics, in the foundations of quantum mechanics, that is still being debated. So what is this collapse? What is the mechanism of collapse? And most of the interpretation issues of quantum mechanics arise from this particular postulate. This is called collapse postulate. And we shall look at one of the important postulates. This is called postulate for evolution. So if we have a state psi of x at time t equal to 0, then the evolution of the state is governed of course in non-relativistic quantum mechanics by Schrodinger equation. Okay. Now the Schrodinger equation is given by this. You have IH cross dou psi of x comma t by dou t is equal to the Hamiltonian operator operating on psi of x comma. Of course, I am talking about one dimension, but this is sufficient to understand the basic issues. So your Hamiltonian is basically when you try to model a system, you always model it in terms of Hamiltonian. Now one can formally solve this equation. Formally solving this equation, you can write down psi of x comma t to be e to the power minus I by h cross into h t acting on psi of x comma t. Okay. Now you can see that since h dagger is equal to h, that means h is a Hermitian operator. Okay. We have u is equal to minus I by h cross into ht is a unitary operator. Okay, it's a unitary operator. Now what happens? It is so you can write down this, what is the definition of unitary operator? Unitary operator, by definition, if you take u dagger or u dagger u, that is identity. That means u dagger is its inverse. U inverse is u dagger. That is called unitary operator. Now suppose if you write this psi of x comma t to be some u of t into psi of x comma 0. Okay, so let us say that let's say that let the initial state, okay, psi of x comma 0. Initially, this is 1. That means it is normalized. It is initial state. Initial state is normalized. Okay. Now what happens? Suppose if I ask what is psi of x comma t and psi of x comma. This is nothing but I have so you can see that I have u of psi of x comma 0 comma u of psi of x comma 0, because that is how the psi of xt is from this equation. But now I know this can be written as u dagger into u psi of x comma 0 into psi of x comma 0. But what is u dagger u? That is identity. It means it is psi of x comma 0 comma psi of x comma 0. So if initially this was normalized, if this is 1, then this is 1 for all. That means the unitary evolution. So you can see that the evolution in quantum mechanics is unitary. That means change in time is a unitary transformation. Evolution in quantum mechanics is unitary, and unitary evolution and preserves the norm of the states. If it is normalized to 1, it will remain 1 for all times. Okay, all unitary transformations will preserve the normalization. So once you normalize the initial state, then you don't have to worry whether as time progresses, whether it will be normalized or not normalized. Okay, so this is one aspect. The other aspect is, so we have to ask the following question: how do we talk about time evolution of how states change with time? Okay, so we can ask this question. Of course, we have written down formally here. The answer is that if you have psi of x comma t, then it is unitarily transformed from its initial state, I by h cross into ht acting on psi of x comma t. So this is a formal statement. Unless I tell you what is the action of this operator, what is the action of this operator on this state, this makes no sense, because it is just a formula. Now, to understand what is the action of this, operator on this, let us try to study two cases. So, case one. Okay, case one. Let's say that h operating on psi of x comma 0 is equal to some eigenvalue e and psi of x comma 0. That means the initial state is an eigenstate of Hamiltonian with the eigenvalue e. Now what happens if this is the situation, such states, so psi of x comma 0 in this case is called a stationary state. Called a stationary state. This word was used by Niels Bohr initially. So now we know that a stationary state means it is an eigenstate of the Hamiltonian. Okay, so what happens if it is a stationary state? Then this psi of xt, x comma t, can be written as, let's expand this operator, that is 1, this identity operator, minus I by h cross into t into h operator. Okay, so let's say plus, I put minus here, plus 1 by factorial 2 into minus I by h cross t h the whole square, and so on. Now this entire infinite series operator will act on psi of x comma t. Now if h psi is equal to e psi, what will be h square psi x comma 0 will be equal to e square into psi of x comma 0. So because of that, you can see wherever h is there, you can replace psi, because h square is going to be e square, h cube is going to be e cube, and so on. So this simply gives you that it is e to the power minus I by h cross into et into psi of x comma z. So that means if it is a stationary state, the evolution is simply the function is multiplied by the phase factor, which is given by e to the power minus IH. So the time evolution is rather trivial in the case of stationary state. Now let us look at case 2. So let's say we have a non-stationary state. It is evolution of a non-stationary state. Evolution of a non-stationary state. So in non-stationary state, what happens? We will not be able to write like this because the state is not an eigenstate of Hamiltonian. Now, because state is not an eigenstate of Hamiltonian, it will not be like this. But we know that H is a Hamiltonian is a Hermitian operator. H is a Hermitian operator. And it has certain eigenstates, and all that eigenstates of H will form a basis for the vector space, the state space. So, if we can find some kind of phi n of x such that H acting on phi n of x is equal to En into phi n of x. Suppose if we are able to find these eigenstates of the Hamiltonian, then we are sure that this phi n of x form a complete orthonormal basis for the state space H. So what we can do, if this is so, then we can write suppose I take phi n of x. Suppose I want to know what is the phi n of x t. This is given by e to the power minus I by h cross into En t to phi n of x comma t. Because each one of these eigenstates will be like in the case 1 that we discussed. So their energy, their time evolution is just a multiplication by a phase factor, where in the phase you will get the corresponding energy eigenvalue. Because of this, and since also this forms a basis, we can write, we can write this psi of x to be sum over n, some Cn into phi n of x. Because since this is a basis, so essentially here I am meaning that psi of x comma 0 can be written as phi n x comma 0. Now I can write down psi of x comma t is equal to e to the power minus I by h cross some t into operator h acting on psi at x0, and psi at x0 is now I am going to write it as sum over n Cn and phi n of x comma 0. Now this is a linear operator, and hence it can go and act on each one of them separately. That means this is equal to sum over n Cn into e to the power minus I by h cross th acting on phi n of x comma 0. But this we already saw that this is a stationary state, and these are stationary states. So we can write down. So this is something that is known from case 1. So that is equal to sum over n Pn into e to the minus I by h cross En t into phi n of x comma. So you can see that the time evolution of a non-stationary state is obtained by the time evolution of the stationary states. Now you can understand why in quantum mechanics, in every problem we try to find stationary states. Because you see whether it is a particle in a box or harmonic oscillator, a hydrogen atom or rigid rotator, whatever problem that you do, you always try to get. So why do we solve? Why do we solve this problem? That is h phi n is equal to En phi n. We are always interested in getting stationary states. Correct? This is called time independent Schrodinger equation. Why you are always solving time independent Schrodinger equation? Because if you know these eigenstates, then the time evolution of any arbitrary state can be obtained by expansion like this. So this is the reason why, because what is the aim of any dynamics? The aim of any dynamics is to start from initial state and try to find out the state at any time later. So that can be accomplished by expanding a given state in terms of the stationary states and then looking at the time evolution of each one of the stationary states separately and combining them in a linear fashion, you get the time evolution of any particular state. So this is very generic, and that is the reason why we always solve this equation. Okay, we always try to get stationary states. Okay, so this is this is a set of postulates that we have for quantum mechanics. There is of course one or two more postulates that we will have to write, but that we will write when the need arises. But I think for the purpose on hand, this much mathematics and the postulates that we have is sufficient. Okay, so now let me make a couple of important remarks, which I did not, I somehow suppressed when I was doing the actual postulates. So I'll try to. So are there some questions at this point? Otherwise, I can.
So,
yeah.
So what is the difference between time evolution and time dependence? Are there any differences between this terminology?
Time dependence and time evolution are same thing. You don't have to worry about that difference.
But I heard somewhere some people were referring it both were different things. So
see, time dependence means, suppose if you say that the state depends on time, that means you should know what is the state at that time t, right? Evolution means it is starting from some initial time, how it goes to final time. Time dependence may be time dependence at that particular time. That could be some small difference that people may be tracking, but I think that's not very serious.
Okay, sir.
Any other question?
Hello.
Yeah, Abhijit?
Yes. Sir, when you are talking about stationary states, that phi of x comma 0 is one of the eigenstate of the system, energy eigenstate.
Yeah.
Certain, even if we don't know, suppose we do not measure a system, so that system is a superposition of all possible this eigenstate, and if we talk about time evolution, then all of these different eigenstates are evolving together with time, according to the last statement.
Correct.
Okay, sir. Sir, one more thing, like the previous postulate, you said that okay, psi of x comma t, psi of x equal to some summation of all of its eigenstate. But, in general, like when we talk about measuring energy, then we think okay, this eigenstate should be sum of all possible energy eigenstate.
Correct.
but when we measure position or momentum, at that time it should be position eigenstate or momentum eigenstate.
Correct.
Then how these two are equal, like psi of x equal to summation of Cn phi n. Phi n is here energy eigenstate, and another one is psi of n equal to Cn summation Cn some chi n, I say, and chi n is suppose position eigenstate. How these two are equal, or is it actually equal or not?
See, normally, even in vector spaces, you know that basis is not unique, correct? You can have infinitely many bases,
Yes.
correct? So a given vector can be expanded in every possible basis, right? So you have a Hermitian operator A, and its eigenstates will form a basis. You have a Hermitian operator B, its eigenstates also will form a basis. So a given state psi can be expanded in A's eigenstates, or it can be expanded in B's eigenstate, or it can be expanded in any other physical observable eigenstates also. Correct? You have the
Yes, sir.
same state, but that state will admit expansion in every possible basis that you can define. It so happens in this case, we are able to relate the basis to the eigenstates of operator, a Hermitian operator.
Okay, sir. One more thing.
Uh,
Is this like measuring, the act of measuring
uh,
is same as that same as some kind of operator acting on the wave function?
no, it's not same, because see, when you are act of measurement is not an operator acting on the function. Act of measurement is something that is happening with the interaction with some instruments, some operators, and things like that. So it's not same as an operator acting on the function.
So, sir, suppose we have a system and we don't know what is the, like, there is a wave function associated with that system. Until we measure it, we do not know the what is the wave function. If we measure it, we get, suppose we're trying to measure momentum, then we know the corresponding eigenvalue, that is the measured value, and the corresponding state is the corresponding momentum eigenstate.
Correct.
So if in real case, so in the actual system, we do not know about what is the sum of, like, cannot talk about. Can you talk about that? This like this wave function is sum of momentum eigenstate. Can you talk about like that? In that, like, because we can measure energy also, we can measure position also, and when we measure it, the wave function become corresponding eigenstate, maybe a position eigenstate or energy eigenstate. But in actual, uh, what is the, like, how can we talk about this sum of these all possible eigenstate? Mathematically, we know. Okay, this suppose we are talking about measuring energy. So we are using the operator. We are using the Hamiltonian operator. So we know this is the corresponding eigenvalue and this is the corresponding state. Okay, but in actual, the system is that may not be in sum of all possible those energy eigenstate. Really?
Okay. So probably, I think your question is quite long. So let me. I think first I have to understand. First, I have to understand your difficulty, and then probably. So let me just try to do this. So let me tell you a kind of a story, and as we develop this story, we will try to understand some of the queries that you have asked. Okay. So let me say that we have. So let's say that we have a system. Okay, we have a system in state phi of x. Okay, and then we are going to measure A, measure A of the system. Okay. Now let us try to describe this process. So we know that A phi n, I'm just suppressing all these x and all that, is equal to A n phi n. That means these are the eigenstates of this. And phi n forms a complete orthonormal basis of the state space H. This implies I can write down the psi of x is equal to sum over n Cn phi n. Okay. Now let's say so this is what I'm trying to describe. So this much is what we know. Okay, what I'm doing physically is I'm just measuring A, and then let's say that we get the result to be, let's say, AL. Okay, so then the state changes to phi L from psi. Okay, state changes to phi L from psi. So this is what happens. Now what you can do, now measure some other property B of the system. Measure some other property B of the system. Now what you have to do, that this phi L, so now we know, because this is another property, we know that there are certain states which I will call it as B chi k is equal to Bk chi k. And this chi k also forms a complete orthonormal basis of H. So what we can do, this implies this phi L is equal to some dlk into chi k, sum over k. So this phi L can be expanded in terms of this chi k. Okay, this is something which we know mathematically. Then let us say that the result, so we get the sorry. So let's say we get the result as, let's say, some Bm. Then what is the state? The state changes from phi L to chi m. Now the state is chi m. Okay. So I have now done two measurements on this. First I measured A, then I measured B. Now let's say I measure A again. Measure A again. Okay. Measure A again. Now I want Abhijit to tell me what do you think will happen. If you are following the story, at this point, what do you think will happen?
Sir, sir, is this like, did you measure B or you have written no measure B of the system?
Sorry, it is not no, it is now.
Okay, okay, sir.
Now measured. So my question is, what is the result? Okay, so there are two options. First option is, I do not know what is the result. I can only say that the result belongs to this set. That's the only thing that I can say. And the other option is, the result is whatever earlier result that we got, AL.
Sorry, should be one of the eigenvalues of A.
So the result should be one of the eigenvalues of A, correct? So this is probably the situation, because see, I have now the initial the state is chi m here. Okay, there is no difference between this chi m and that psi. Correct. Initially, we had a psi, and so when we first started, no, I had psi here,
Yes, sir.
and I had got one of the result. Now I have chi m here, so I will get one of the results again. Okay, but sometimes the result will also be A. Okay, so this case also occurs if these two operators commute with each other. Okay, so this aspect I did not discuss today, but if they commute, it is possible that they can have common eigenstates. That means the if this, so essentially A we have observed and got AL, and the state was phi L, and when you observe B, the result of the previous measurement will not be disturbed. If they don't commute, then the result will disturb the previous state, and you have only this situation. That is, if your A and B don't commute, if these two operators don't commute, then this is the situation. If they commute, then the result can be AL itself again. So this is what happens if you have this sequence of measurements. Now, I think your question had another component. The component is, let's say that we have psi of x. I mean, this is as far as I have understood. So let's say you have psi of x. This is the state. Now, let's say that you measure A. Okay. Now, let's say somebody else measures B. Or you want to measure A and somebody else want to measure B. Okay. Now the point is, if you are approaching this system with your A meter, okay, let's say you want to measure A, so you are taking your A meter and approaching this system. So for A meter, psi of x appears as sum over n Pn phi n. This is how this appears for A meter. On the other hand, for B meter, psi of x appears as sum over some k, dk, ik. So whichever meter are the apparatus that you are saying, the psi of x will appear differently for this state. Essentially, it means that the corresponding eigenstates, so this state gets itself resolved into the corresponding eigenstates, and that is what leads to appearance of one of the eigenvalue for A and for B. So imagine that, let's say that I have two identically prepared systems. One system I will send it to you, you measure A. One system I will send it to your friend, he measures B. So it is the same psi of x that is going as input state for both the measurements, and you will see that you will get one of the result as one of the eigenvalues of A, and he or she will get one of the result as one of the eigenvalues of P. So this is what I think, as far as I understand your question.
Yes, sir. Okay, sir. So are we allowed to talk about what is the actual psi of x consist of? Like what it appears to as B meter or A meter. So we cannot say for sure what is actually psi of x made up of.
See, psi of x is having a unique identity. There is no doubt about it. It is some vector in the Hilbert space, correct?
Yes.
Now, depending on what you are trying to measure, you will resolve it into the components of those respective operators. Correct? Otherwise, independent of what is the choice of your basis, this psi of x is it has its own identity. In fact, this identity is what I did not introduce. So probably in the next class I'll introduce this particular fact that what psi is independent of all this choice of bases is what you call as the state. Okay, and this is what you call as a ket psi in Dirac notation. Ket psi is something which is independent of the choice of basis. Okay, so what is psi if you are asking? That is basically a Dirac ket. That is an abstract vector in the Hilbert space. Now it will become psi of x if you choose an x basis, or it may become psi of p if you choose a p basis, or it may become psi n if you choose some energy basis, and so on. So it is only the choice of basis that will take that abstract vector into some concrete component form. Otherwise, that abstract vector has its own identity.
Okay, sir. I understand.
Yeah. Any other question?
Sir.
Yeah. Hari?
Sir, in the class you mentioned that the quantum operators are Hermitian. Is there a chance that a operator can be non-Hermitian? Or is that a possible?
Operators can be non-Hermitian, but physical observables have to be Hermitian.
Okay, sir. So if physical observables, because they are real, so we need a real Hermitian operator to measure them. So is that the reason why we are using classical probability to express quantum mechanics? Because it's we're using a Hermitian operator. Is that the reason, or any other reasons there?
No. See, usage of probability has got nothing to do with the choice of Hermitian operator. The Hermitian operator we are using because there is a connection between the measurement results and the eigenvalues.
Okay.
So you have to have the measurement results to be real numbers. Correct?
Okay. Yes, sir.
The probability is coming because of the interpretation that we have the wave function as a probability amplitude, right? So
yes,
there is a kind of uncertainty, and since we will not be able to say anything for sure, so we have to use the language of probability.
Okay, sir. So one more question. We discussed here the time evolution of a quantum state. Yeah. So we use the energy Hamiltonian operator, which is a unitary operator. So
Hamiltonian is not a unitary operator. Hamiltonian is a Hermitian operator.
okay.
E power minus I by h cross into ht is a unitary operator.
Okay, sir. So we expressed the wave function with the e power I by h bar with the eigenstates of the energy eigenstates of the system. So can we find the time evolution with the momentum and momentum eigenstates or the position eigenstates in the same way? Can we do that?
No, I think I'm not sure if I understood your question, but let me pretend that I have understood and then answer. And if I'm not answering your question, I think you should tell me. So I think the question that you're asking is that suppose if you have psi of x comma t is equal to e to the power minus I by h cross into ht into psi of x comma 0. This is basically this is Schrodinger equation. This is coming from Schrodinger equation. Correct?
Yes, sir. Yes, sir.
So now, if I understand your question, you are asking, can I change this h to p or is that the question?
X. Yes, exactly, sir. P or X. Yeah.
So we cannot change it here because this is coming from the Schrodinger equation. Schrodinger equation is IH cross dou psi by dou t is equal to h psi. Correct? So this is h here. So we cannot change this one because how am I getting this? I am trying to say, okay, d psi by psi is equal to minus I by h cross into h into t. Here, of course, I am into dt. I am assuming that h is not depending on time, so I integrate on both sides, and then I will get logarithm of psi here, which is equal to minus I by h cross into t into h plus some constant, which I will call it as logarithm of c, and that is how I will get the c will be the initial wave function, and that is how I am getting this. So this h here has to be h only; it cannot be anything else. Okay, that is what we say. H governs the time evolution. Governs the time evolution. Okay, or sometimes you call this as time translation. Okay, but your question has an interesting consequence. Suppose if I have some, let's say I have some function psi of x. Okay, I want to do a translation in space. So let's say I want to take this from psi of x to psi of x plus a. Okay, just like I am taking 0 to t, I want to take x to x plus a. So you can ask a question, what kind of operator will do this? Okay, suppose let's say I want some unitary operator doing this job. So what is this unitary operator? You can ask that question. That question can be answered. For example, suppose if I take this psi of x plus a and then do a Taylor expansion of psi of x plus a into d psi by dx plus a square by factorial 2 into d square psi by dx square and so on. You can see that this can be written as 1 plus a d by dx plus a d by dx the square by factorial 2, etc. This operator acting on psi of x. Now you can immediately notice that this is an exponential Taylor series. So it can be written as e power a d by dx operating on psi of x. So the operator that does this job is e power a d by dx. But we know that your momentum operator in one dimension can be written as minus IH cross d by dx. This is a Hermitian operator. So I can write down this d by dx to be I by h cross to t. So you ask the space translation is affected by a unitary operator which is e power IH cross a into p acting on psi f x. So we say that the momentum operator governs space translation. Okay. So a similar operator with a linear momentum will not do time translation, but it will do a space translation.
Okay, sir, it's clear. Thank you.
Any other question?
Sir.
Yeah.
Hello.
Yeah, Avinash, still.
So in the earlier section, yes, sir, so that we can dissolve any wave function in form of its eigenbasis, and whenever we do an operation, we measure one of its eigenstates.
Yeah.
So when we had like that one of the equation we had two eigenstates, and one at probability 1 by root 3 and another at root 2 by 3. So classically, if I have a state like if I have a bag with two balls, I'll have the probability of getting either of as 1 by 2.
What is your classical system?
If we had two states, so like head, if I had a coin, either I'll get a head or a tail. Like the probability associated will be 1 by 2. But here we have probabilities like if I find the probability of getting that state, I get 1 by 3 and 2 by 3. So if I was like continuously doing that experiment normally in a classical system, so if I do it 1 time, I get it 500 times. But in quantum mechanics, it's actually telling me that I do it 3 times. The probability getting 1 is like the first state is 1 by 3. So it's as if like if I do another measurement.
No, what I'm trying to, so here, what I wanted to tell you is that these coefficients, what I have written, they are just for example only. Instead of 1 by root 3 to root 2 by 3, I could have written 1 by root 2, 1 by root 2, then it will exactly correspond to what you are saying, right? If I have taken 1 by root 2, 1 by root 2.
Yes.
So what I'm saying is
that you give also. Yes.
What I'm trying to say is that those coefficients you don't have to take very seriously, because those coefficients, so I could have simply said that my phi of x to be, let's say, some cos theta times, let's say, I think I wrote a psi 1 of x, right? Plus sine theta times psi 2 of x. I could have written like this. All that I require is cos square theta plus sine square theta should be equal. That's anyway 1. So theta can be any value between 0 and 2 pi. This is a possible state for me. Then your probability of E1 will become cos square theta, and probability of E2 will become sine square theta. Okay, the particular example that I have given corresponds to, I don't know if it is what kind of theta it is, 1 by root 3 and root 2 by some theta, it doesn't matter.
The question exactly is like quantum mechanically, this in this combination, theta can have any value, like such that psi can get any process that like overall it's based. But if we consider that, we are indirectly saying that if we are fixing like if we fix that initial probability,
I'm really sorry.
If we only have two states, the probability.
Avinash, I'm sorry really because I could not hear your question. Your voice
So is it
breaking.
audible now?
Now it is audible. Okay.
I think there's a delay also because since it's raining over here.
Delay is no problem, but it was breaking and discontinuity was there.
Okay. The doubt is if we classically have one system, like a system where there are two states, we get the probability associated to each is half for sure. Like we can't change it. Like even statistical mechanics, we counted the total and we had.
No, that is also not true because see, our coin toss, we may say it is half-half, but we can also think of some biased coin where you will get three times more head and 1/3 times as the tail. That is also possible. So this the choice of probabilities is it depends on your system. It's not that in classical system it will always be half-half.
What we are counting instead of like having a system, like if we count, if like in a system where there are like two balls and we are finding the probability of getting one of those balls, so there it has to be fixed, right? Like we can't, even if we put a bias, if we assume a system where there is no bias, like, trying to point here is like we are measuring something and it is in somehow affecting like the next probability. Okay.
Yeah, that is your next probability means the second measurement that you are doing. That's what you are saying.
Yes, because otherwise it should have been half. Like if we have or like normally if we don't have an unbiased system, it should be 1/2 or something which we can't fix. But when we are saying it's something which is like 1/3 or 2/3 or cos theta sin theta, where it's not 1/2, we are indirectly saying that it's we are measuring it, and the next measurement is based on what we measure.
Okay, so let me just give you one more example, then this might clarify. This is more classical example, but it has something similar to what we are discussing. Suppose, let's say that we have polarized light. Okay, you know this light is polarized. No? You represent it like this, plain polarized light. Suppose if you are passing through an analyzer, which makes an angle, let's say, corresponding to this and this, the angle is, let's say, theta. Okay. So what happens, you know this Malus law, this famous Malus law. Malus law tells you that if this is the intensity of the polarized light and this is going to be I cos square theta. Correct? The intensity will be reduced. Correct? Now you can see that depending on this theta, now you can ask a question. Suppose the same experiment you are trying to do, but let's say you are just sending a single photon. Okay, one photon you are sending. Now what happens to one photon? This photon will either be transmitted or it will be reflected. Sorry, it will be absorbed. Either it will be transmitted or it will be absorbed. So that can be understood when. So now, if you think this particular polarization state as some kind of a cos theta times the parallel direction to this analyzer axis plus sin theta times the perpendicular direction to that. If it is perpendicular, then it will not go through; it will get absorbed. Okay, so that means it is like this. So depending on this theta, you can have any bias, right? If theta is equal to 0, then that means this is the total thing. If theta is equal to 90, it is complete absorption. But depending on your theta, you can have any bias that you want. Based on that, the intensity of the light on this side will be determined. So essentially, what I'm saying is this 1/√3, 2/√3, whatever I have said is one such example.
Okay, sir.
So I think we have almost closing in to the time, and I would say that these postulates are completed, and you can go through these postulates, and when we meet next time, so I also would like to get some feedback from you. Let me just there was a question in the chat box. 1 minute, Abhijit. Why the system restores itself to the same state when the system is. Alip Mahapatra, are you there?
Sir, he is there. He said that his microphone is not working.
Okay. So I thought if he is there, I can. Let me read why the system restores itself to the same state when the system is. Okay, so I think if I understand your question, you are asking if the operator is dispersed, then there is a loss of information. If the operator is sharp, there is no loss of information. Okay, so that is understandable because it is like just like this example I gave. I think this example will help you to understand this. Suppose if if the polarization direction of the photon is this one, that means if theta is equal to 0, then a transmission with probability 1. So there won't be any change in the polarization state after that. There is no loss of information. In this case, there is no loss of intensity here. Okay, but if theta is not equal to 0, then there will be a probability for transmission, there will be a probability for absorption. Okay, it is like that. That is why if you are starting with eigenstate of the operator, there is no change in the state. I hope that was the question. Yeah, you have something to say, Abhijit?
So I was saying that there is one question remained in the chat.
Yeah. I also saw it, but I forgot momentarily. Okay, then we will close and then meet next Monday.